In this video, we're going to be discussing angle bisectors in triangles. Ray BD is the angle bisector of angle ABC. Looking at point D, if we were to draw points or line segments ED and DF, we would find that they are equal in length. Recall from chapter 3 that the shortest distance from a point to a line is the perpendicular length between them. That's why that right angle has to be there, to indicate that that is a perpendicular. It's the shortest distance. If I were going from D to A, that would be much longer. If I were going from D to here, that would be slightly longer. The shortest distance, and that's what we're going to use, is from D to E, and it's perpendicular. Angle bisector theorem. If a point is on the angle bisector, so any point on ray BD here, is equidistant from the sides of that angle. In other words, if line BD bisects angle ABC, BE is perpendicular to ED, and BF is perpendicular to DF, then ED is equal to DF. A little wordy, but hopefully you get it. The converse is also true, that if a point is in the interior of an angle and is equidistant from the sides, then it must lie on the angle bisector. So right here, I see the right angles, which tells me that from Y to Z and from Y to X, that's the shortest distance to that side of the angle. And it shows that we have a 6 for the Y to Z, and we have a 6 from the Y to the X, which means they're the same. And the question asks, is Y on the angle bisector of angle XWZ? The answer to that is yes, because Y is equidistant from the sides of angle XWZ. It must lie on the angle bisector. The angle bisector is not drawn here, but what we're saying is that if we did draw it, then it would actually be on that angle bisector. Ray MO is the angle bisector of angle LMN. Okay, that means that any point on ray MO, like O, is equidistant from the sides. So since we see the right angles here, we must know that these two segments would have to be the same length. So OL is equal to ON. In other words, 4x minus 5 is equal to 23. Now we simplify and solve. I guess there's no simplification, we just solve. Add 5, 4x equals 28. Divide by 4, x is 7. Now we're going to find the angle bisectors of a triangle. Every triangle has 3 angles. We're going to bisect each of those and see what happens. We should probably use a protractor to find that. You actually would use a compass and a straight edge, but we're going to keep it a little simpler here. So I'm going to measure angle A. Angle A is approximately 55 degrees. I have it a little wider than it needs to be. So I'm going to go half of that. Half of 55 would be 27.5. So there's 27 5, 6, 7-ish right there. So I'm going to go from the vertex A to that point. That would be my angle bisector. Okay, I'm saying that this is congruent to this. There's my first one. What is true about every point on that orange angle bisector? They are equidistant from sides AB and AC. That's what's true. So if I picked a spot like right here, the distance perpendicularly right there would be the same as if I did it there. And that's really important to understand. Okay. Let's measure another angle here. This one looks like, this thing's not that easy to use. 36 or 7, 36 we'll say, so 18, that would be halfway. Looks about right here. I'm going to draw an angle bisector for that angle. So what I'm claiming is that this is congruent to this. Looks pretty good. And what is true about every point on that angle bisector? They are equidistant from sides AB and BC. And technically we have enough markings now to state what I really am wanting to state, because we do have an intersection of those two, which means they have a point in common. But we're going to go ahead and do the third one here. Looks like, well, it's really close to 90 degrees. Let's go ahead and just call it 90 degrees. So 45. I think I'm done with this guy. From the vertex to the dot I made. And what do you know? They intersect all in one spot, which means we have another point of concurrency. It's right here. What is true about every point on the red angle bisector? They are equidistant from sides AC and BC. So this new point that we just found, the intersection of all three, the point of concurrency, it's called the incenter because it's the point of concurrency for the angle bisectors. And what must be true about that point? Point D is what we've labeled it, or what we were suggested to label it. Point D is equidistant from all three sides of triangle ABC. So that is what the incenter is. It's this single point that is equidistant. So the distance from A to B perpendicularly, from side CB perpendicularly, and side CA perpendicularly would all be the same distance because of the incenter, because we found the incenter. Very important to understand. And we will have to memorize that. So now, thus far, we have talked about 2 points of concurrency. The first of which was the circumcenter is equidistant from the vertices of the triangle. To find it, draw the, how do we find it? We use the perpendicular bisectors. Okay, and I'm gonna try to do that pretty quickly here. I'm just gonna eyeball it a little bit more than I normally would. But we find the middle using hopefully a ruler usually. And then we go perpendicular to that side. I'm gonna draw it perpendicular first and then move it because I can. You guys could use a ruler to kind of make it perpendicular. Okay, there's one. And again, this may not be perfect as I am just kind of eyeballing it. The middle looks around here. And we're going to draw a perpendicular line. That looks to be pretty perpendicular. Make sure it goes through the midpoint. And then we're going to do this one more time just to make sure that that point of intersection, we hope, is my circumcenter. So find the middle, maybe about right here. Draw a line perpendicular to that side, and then make sure it passes through the midpoint. So then I have the ability to move it. And it looks like I'm a little off. So what I'm going to do is just make it closer and move my midpoint a little bit. Maybe I was a little off on one of those 3. And make it perpendicular. And so what we have here is the circumcenter. And this was outside of the triangle, which can happen. In fact, for a circumcenter, it might be inside, outside, or actually on one side. If it's an obtuse triangle, it'll be outside the triangle. So because of this obtuse angle here, this one wound up being outside. An acute triangle to be inside, and for a right triangle to be actually like lying on one of the sides of the triangle. I think it'd probably be the hypotenuse every time. So now the other part here is the incenter. Okay, it is equidistant from the, this is what we just learned, equidistant from the sides of the triangle. To find it, we draw the angle bisectors. And again, I'm going to eyeball this more than I normally would. Just kind of what looks like the middle. That looks like the middle of that angle. That looks pretty close to the middle. And that looks pretty close. So that was a lot easier to just kind of eyeball where that is. So this is the incenter. Of course, that would only be true if this angle is congruent to this angle, these 2 angles being congruent, and these being congruent. The incenter is equidistant from all the sides. Make sure we understand that. And it will always be inside the triangle. So now that we know when we have an incenter what it means, hopefully we can apply that on our assignment. If you have any questions, please let me know.